All right. Yeah, so good morning, everyone. Yeah, I guess welcome to the final day of teaching. So we're going to continue learning a little bit more about simulation-based inference and its applications. So hopefully you remember something from what we discussed on Friday about SBI. That's good because, yeah, what you learned on Friday will be relevant here. So this time we're going to look at simulation-based inference methods for unfolding. So what is unfolding? The physics that we care about and that we study at, for example, the LHC, but in any high energy physics experiment, you're actually looking at, you care about the fundamental interactions, but you never actually measure them, right? What you measure is really the decay products going through your detector and making some measurement, and then it has some, it might have some biases in your detector, but more importantly, it might have some smearing from your detector. So if the true width of some distribution is really small, then the detector smearing will make that width much larger, right? So what you reconstruct from the detector, these distributions include detector effects. Whereas you might sometimes want to unfold those detector effects. So remove those detector effects and try to guess what the actual distributions would have been like if your detector was perfectly precise, for example. And this is important to communicate our results from experiments to theorists. Why? First of all, there's so much, a lot of details in an experiment that you don't want a theorist to have to know to be able to analyze our data. And they might use it to directly compare some new theory model with this unfolded data without having to do the full detector simulations. Also, for example, combining limits from multiple different experiments, and not just experiments, also from cosmology and so on. So you want to combine all of these things. Theorists spend a lot of time doing that. And for sure, you don't want to have to worry about the detector effects in every single experiment when you're doing that combination. So this is why unfolded results really helps. The other thing is reanalysis of old data. For example, when an experiment ends, of course, experimentalists move on to a new current experiment. And so you won't always have a whole bunch of experimentalists waiting for you if a theorist says, wait, I actually want this kind of observable from this old experiment, you will not be able to do that. So once you unfold your data, it becomes much more usable. And anyone new can pick it up and use it without having to worry about all the detector effects. And this is used for things like Monte Carlo generator tuning itself to make these simulators match data better, also for a Partha distribution function and all of this. And often they will combine data coming from different experiments to tune these simulators better. Now, traditional methods of unfolding have some common features. So there are different methods that I won't go into. There's IBU and matrix inversion and so on. But they're all binned, which means that you first need to choose a histogram that you want to unfold, choose an observable that you want to unfold, make a histogram of it, and then you can unfold in those bins. Of course, then the thing is, the binning you choose in that like in your experiment today gets frozen for eternity, right? So if in the future a theorist says, "Oh, I actually wanted finer binning here, and I don't care about the binning here," it's lost. The other is that it's only one-dimensional. So the observables you choose to unfold today are the observables that will remain preserved. But in the future, if you realize that, wait a minute, I don't want x and y, I actually want x squared minus y cubed or something, since everything is histogrammed and stuff, you can't really get a nice distribution of this higher level observable. Or even if you just want the same observable but in a different, like if it's linear and you actually realize that you want the distribution in log space, you can't get that unless you can convince a few of your experimentalist friends to go back and unfold that distribution. And the later it gets, like if it's 10 years down the line, it's highly unlikely somebody will do that for you. But it's worthwhile to keep in mind that unfolding is not a straightforward problem. It's not an invertible function. So if you take some mad graph plus like hadronization is done, and then you just do a detector simulation, you can't just go backwards because this is a many-to-many function. And so even though we do try to do this inversion, it's not a fully constrained problem, and so you need to add additional constraints to do this. Often it's in traditional methods you would put smoothness regularization, because if you were to just blindly do maximum likelihood, then you would see that the distribution becomes super choppy to try to maximize things, and that's not what you expect. So you put a smoothness constraint. So let's see an example of where a real life example of where actually ML unfolding might be useful. So here we're talking about this result from an old experiment, which was, so there was this observable that was unbinned using the traditional methods in linear space. And then some of our theory colleagues realized that they actually would like to see this in log space. So this is the result from Aleph. And so I think this green is the original unfolding. So you can see that if you turn it into in this log space, then suddenly the first bin becomes huge, and then everything else is over here. But this is where the interesting physics is happening, and so all of that is lost in the single bin. So in this case, an ML unfolding was done. This red one here, and since it's intrinsically unbinned, you can choose any transformation and then bin it in there and make these histograms. So of course you see the red one is also a histogram, but it's been histogrammed after unfolding. So you can change things up and things still work. And then you can compare this to various simulations. And so of course you can see that the black over here is the actual data. And this is with detector effects, and then this is without detector effects. There's a significant shift that happens, and you need to get the shift right, and only then can you compare to your different theories and see if the data is putting any constraints. Does this make sense? Okay, so if it does, then now I'm gonna pose a question to you. It looks very nice, right? That you can get these unbinned, unfolded results. And I'm saying that with machine learning, you don't have to restrict yourself to one observable. You can do multiple observables simultaneously. Anybody have an idea of how we might be able to do this? You've learned all kinds of models till now. Is there anything that you think could predict the true distributions? Yeah. So that's the thing. Like, besides the architectures, we need to also start thinking about how to use these models to solve the various different physics challenges that we have. Yeah. Generative. Okay. So the first suggestion is generative. It's a very good suggestion. Are there any other suggestions? Okay, let's start with the generative one. But okay, before that, let me just bring some context, just to make things a little bit easier. Maybe it helps you guess. This is what we want: the truth of nature. We don't have this thing, but we have three other quantities. We have the RICO data, right? This is what we observe in the experiment. We have Geant4 simulations of the detector, and we have, before the Geant4 simulations, the generator level truth. Okay, if we believe this to be exactly right, then we don't need this, then these two are the same. But we think this is not the same as this. That's why we want to predict this. So yeah, so these are the three things we have, and from the three quantities we want, at maximum we can use the three quantities to predict this fourth quantity. And as rightly pointed out, one possibility is generative models. So what would you do there? Out of these three pieces, you would train. So you have a detector simulation here, and without detector simulation here, right? But you have labeled, this is simulation, so you have everything. You could train a generative model to go from here backwards towards this, and then maybe apply the same thing on RICO data, and then you predict this, right? That's an idea. There are problems of doing this just naively, of biases. Basically, any biases in your simulation will translate into your unfolding, and then this prediction will be biased. But we'll look into that after a few slides. But yeah, this is a promising idea. The challenge is generative models are have to really learn the distribution from scratch, right? So most generative models that you're aware of, they start from some kind of a very simple noise distribution, and they have to map it to this physics distribution, which means they need to get the whole distribution right, including the tail and so on. It's challenging, especially for our kind of data sets. And so flows were used at some point, and recently we put out a paper using diffusion models. Particularly, these models are called latent diffusion models, where the idea is, so you have the detector information here, and then you have something like a variational autoencoder here. But in the latent space, you're doing diffusion. So, and that is conditioned on the detector effect. So you allow, so yeah, this detector encoder is used to do the diffusion, and then it's unfolded to this was done for partons. In reality, you would do it for particles. So this is one example. And here we start to see that generative models are coming to the point where they can actually be used. Yeah. Yeah. Okay. So yeah. So the generative model session is coming up after this one. So there we will learn a little bit more. But essentially, the idea of diffusion models is that you do the diffusion process. So let's say for images. So this is how it was originally used. You have some images. You know that if you successively add a little bit of Gaussian noise to it, you can corrupt any image to the point where it then diffuses into just white noise. And this process is reversible. So if you can learn, if you do the forward process, you can learn to do the inverse process over multiple steps. So this is unlike GANs or VAEs that do a one-shot prediction. This does the reverse process in multiple steps, and then you can go from white noise to your actual data distribution. That's a normal diffusion model. Here, the difference is that you have over there, conditioning on certain things is a bit challenging. So you could use the network that's doing the inversion, you could condition it on the detector observables. It works for a few, but when you have a whole bunch, like here we want to unfold something like 55 different observables, it doesn't work so well. So in fact, I think the LDM is that model, this kind of the typical diffusion model, and you can see that so the truth, okay, these are small plots, unfortunately, but the truth is in blue. So the top are the plots and the bottom are the ratios. And you can see that the LDM doesn't do a very good job at all of reproducing this. And then this this INN over here, these are the state of the art normalizing flows before diffusion models were tried. But with this yellow one, which is our proposal, it does the best at modeling the truth. So you can see that the yellow one has the smallest residuals, but still they do exist. Anyway, so here what happens is you have, this is like an autoencoder. So you take the pattern, the truth level distribution, and you encode it and you decode it. But in the center, instead of just having a Gaussian thing, you do, so you can take whatever the encoder has done and diffuse it all the way to noise, and then bring it back, and then decode it. And we see that this method, and then the fact that you can train all of these three networks together lets you get this improvement in performance. So the point here is, okay, we have a lot of these metrics, and we see that by doing this kind of diffusion model, we really beat like by quite a lot the state of the art, and we start to move towards this a level of performance which you might be happy with for unfolding, and especially for very extremely high dimensional unfolding. So there are some ML methods that work well for a few dimensions, like a few observables, 5, 6. But for extremely high dimensions, you need extremely powerful models. So diffusion looks promising, but this model is not ready to be used in an experiment yet because of the biases that I talked about. Right. There's a way to remove these biases that we're going to talk about next. But first, think of this problem. Like you said, there are existing solutions in the machine learning world for a lot of these problems. So instead of trying to invent something new first, the first thing to do is look at what exists and see if something will just work out of the box. There are super resolution methods that have been around for a long time, right? You take this coarse image and then the neural network gives you this high definition image, right? And then you've probably seen this one as this pixelated image of Obama, and then as soon as you apply super resolution, whoops, right? So this is a clear example of if your training data set is biased, then the application will also be biased. And this is exactly the kind of problem we do not want in our physics data sets, which means that if you train on simulations and simulations are doing something different from data, then we will unfold in the wrong direction. And this is precisely why in this kind of problems, we don't want to use off-the-shelf ML solutions and want to develop our own solutions. And so there are a set of iterative ML unfolding methods that can handle these biases. So again, they will use, so we want to predict this, and we have only these 3 samples. These are simulations before, after detector effects, before detector effects data. And I will talk about we talked about generative models. Now I'm going to talk about this other method of doing it, which only uses classifiers. But the point is, so let's say this blue is your prior, right? So this blue comes from your bias simulation. And the green is the truth, which in reality you don't have access to, but in our experiments, we're pretending we have access to this. And when you do a simple, like a naive unfolding, your prediction in red will coincide with the prior, so your bias, right? But I will show you an iterative method via reweighting, which over multiple steps starts to move towards the truth. And by the end, reproduces the truth. And the key thing here is that you do not have access to this truth. You never use this for training. Because if you did, you're cheating. You won't have this in real life. So you need to somehow leak information from the data into your simulations and correct your simulations in a way that you can do this. How does it work? This method is called Omnifold. It was published a few years ago, and it's very successful. It's been used in some experiments. I think LHCb used it recently, and some H1 and just the Hera experiment has been using it quite a lot. So this is the idea. You do 2 steps of reweighting. And you always train apples to apples. So you have both of these here are after detector effects. So first thing you do is you reweight the simulation, look exactly like the observed data you've done, you've recorded. How do you do this reweighting? If you remember what we learned on Friday, you can just train a classifier. Yeah, you can train a classifier between this and this, and take the output of the classifier to estimate the likelihood ratio, and then reweight the simulation to look exactly like data. But that's not the end. So, and the other neat trick is you have a one-to-one correspondence between your simulation and your generation, because that's how you've done it, right? You've taken your generation and then applied GN4 to get the simulation. Does that make sense? There's a one-to-one correspondence between events here. So if you have a weight for an event here, you can just pull the events back and say, look at the generation distribution now with these weights, right? And then you do a second reweighting, which is not between these two, by the way, because this you don't have access to. It's a reweighting between this and itself. So you take the weighted one and the unweighted one, and you train a classifier between them, and then you get a new set of weights. And you use that for the generation now. Why are you doing this? This is the iterative part of unfolding. As I said, there is no one exact solution. And so when you do this reweighting, you find a new set of weights that also describe the same distribution at the generation level, right? But there are a new set of weights, but the distributions look the same. But now we push these weights back to the simulation, and at the simulation level, the distribution looks different. Because just because these distributions look the same doesn't mean these distributions will look the same. And then you see that there's actually now a discrepancy between data and simulation again. So in the second iteration, you do this reweighting again. You make the simulation look like data. Pull, reweight, push. And you do this many, many times. And when does this start to converge? When you find a set of weights which is which becomes stable over this multiple iteration. So you can pull and push, and it's still the simulation continues to look like data. So your reweighting will really just give you ones at the end. The likelihood ratio will be 1 everywhere, right? Okay. In theory, the convergence happens when you run infinite iterations. In practice, up to 10 is more than enough. And in fact, as I said, if you keep, so the more times you do it, the more you're maximizing the likelihood, but that's in an unconstrained problem. You don't want to do that too much because you need some kind of regularization. In traditional methods, you explicitly added a smoothness constraint. Here, just the fact that you don't go to infinity and you stop the thing at 10 or earlier itself acts like a regularization. So these are the results from the original paper. So here, the green is the truth, which you wouldn't have in real life, but here they've just used a different simulation for the truth. And so yeah, and the green, sorry, the blue one is your generation. So it's your, so if we pretend that the green is data, then the blue is your simulation, which includes the bias. So you can see that the green and the blue don't match. And then both of them after detector simulations go to, the black one is your data and the yellow one is your simulation with detector effects. And after doing these multiple iterations of reweighting between yellow to black and then blue to itself, you get this red distribution, which reproduces the green one very, very well. So that's the key message to take home, that even though you don't have access to the green distribution, you can model a green distribution using the other three. Yeah. Yes, yes, yeah. These are terms that we use in the original paper. Just means copy. It just means copy because you know that how you do the simulation is you do mat graph generation and then pattern showering harmonization, right? That's here. And then you'd run Geant4 to go from this event to this event, right? So these two are the same events just before detector and after detector. So if you have a weight for this event here, you know the corresponding event here, so you just copy over the weights. That's called pull. And when you copy this direction, it's called push. Okay. Yeah, so you have some initial weights here, but these weights will be the same as these weights, right? The detector simulations usually doesn't add any weights, right? So in the beginning, each event here and here have the same weights, but then this one is reweighted. So now this has new weights, so then you just go back and see what the distribution would look like here. Mm-hmm. 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 That's right. Yeah, that's the step one. In step two, you will compare the new weights with the previous weights. So like originally is the weights coming from MC, then it's the weights coming from the reweighting in iteration 1, then it's the weights coming from iteration 2 and 3. So you're always comparing the last two set of weights. Push just, yeah, it's extra. I mean, forget about push and pull. It's just, the weight for the event here and the weight for the same event here should be the same. That's all I'm saying. So as soon as we get new weights here, I'm just saying that that reflects in this distribution as well. Yeah. Let me think about that. This is for unfolding. You are saying how? How would that? Maybe. Yeah. Mm-hmm. Yeah. Yeah. You can tune it. Yeah, so in principle, yes. So once you get the unfolded, and that's what you do, you take the unfolded distribution and you use that to tune your Monte Carlo generation. Absolutely, that's right. Yeah. So then you would, like, if there are some free parameters in your thing, you will tune them so that generation for free looks like this unfolded distribution rather than having to do the reweighting. Yeah, okay, that's right. Yeah, parameter, like tuning the generator is only one of the many things you do with unfolded results. Of course, in data, you don't have as much simulation, so each individual like experiment gives you only a small constraint, and then you have to combine from different ones. Mhm. What are the other questions? Okay, if you don't ask me questions, I'm going to ask you questions during the tutorial. And so yeah, I encourage you to ask. This is not an easy concept. It even the students at Berkeley who work on this, it takes them a few months to get the full concept in their heads. So it's, yeah, please feel free to ask. Yeah. The generation is imperfect, and therefore the simulation, the distributions in the simulation will be imperfect. But we are assuming that Geant4 is perfect. Yeah, that's a very interesting question. What if your detector simulations are also imperfect? How do you invert the detector effects if your detector simulations are imperfect? You can't do it with this. This requires the assumption that your detector simulation is perfect. How can you do that? Yeah, we'll have to think about it. Maybe we can chat afterwards. But yeah, not just by applying Omnifor for sure. If you want to do that, then you have to do element by element separate. Element of the detector. You can't do the entire detector because one number describing the whole detector, or one bunch of number describing the whole detector is cross average. Okay, but this works. So in fact, yeah, you can't fully correct it, but what you can do is, so you can parameterize the places where you expect the detectors to be wrong as your nuisance parameters. Yeah. So like jet energy scale calibration or something. And then there is a way to do this unfolding, including nuisance parameters, which I haven't mentioned because it's very new and confusing. Yeah, and then what you would do is you would, this maximum likelihood thing that you're doing here, you would do it both for this step plus your maximum likelihood for what the nuisance parameter would be. So you're fitting both the nuisance parameter and the unfolding simultaneously. Right, yeah, okay. So we are getting somewhere. Yeah, so that paper came out just a few months ago, I think earlier this year. Yeah. Yeah, okay, and then you can collect the detector. Yeah, so each element might be miscalibrated, but they're miscalibrated. Usually the effect is the same, so you, instead of having to do 100 million sensors, you can bring it down to a few nuisance parameters. This one time, you know that which detector gets point out quickly, the front side, so the high flux. So one knows that there we need more correction than in the transfer. Yeah, absolutely. Yeah, you can parameterize all of that. The question is very realistic, I would say. But one cannot do one range fits all kind of stuff. Yeah, yeah. So the more uncertainty you have over the detector simulation, the less power you'll have in the unfolding. So of course, after this also you get the uncertainties of your unfolding, which come from so if you have 10 events, your unfolding will be not as powerful as if you had 1,000 events. And so yeah, these uncertainties will be bigger if your uncertainty on the detector simulation is high. Okay. So yeah, I'm going to move on now, but if you have more questions, just interrupt me and say, oh, I forgot about this thing. Yeah, because this is important. Otherwise, we will not be able to, you will not fully digest the tutorial that we see afterwards. Right, so just to conclude, unfolding away detector effects allows to use experimental data more better by a larger community. And traditional methods can only do binned and single dimensional unfolding. With ML, you can do very high dimensional unfolding. Even you can think of trying to do the whole phase space without binning. which means you are able to keep more power. And since you're unfolding multiple observables, first of all, each individual unfolding is more powerful because if there are correlations, it learns that. And you can, since the unfolded results are multidimensional and unbinned, you can plot them as you like afterwards. So it's much more useful for not just tuning, but also just setting limits on some model afterwards. And we saw an example of that where we had to transform something from linear to log scale, and it was only possible with ML. Okay, so I did. Oh, right. So then and it can also handle biases in your generation and simulation itself. And as we discussed, also nuisance parameters. Okay, now we're going to switch to a tutorial where we actually do this kind of unfolding, not with a generative model because it takes too long, but with this omnifold, which is anyway the more popular one to use. Okay. So hopefully you guys have pulled or cloned the latest version of the GitHub. So I'm talking about this over here. So yeah, if you've made changes already and you want to just discard it, you can do that and just git clone this again. And hopefully by now, the pen drives have reached most of the people. Is there anyone who hasn't got the data set yet? Oh, wow, a lot of people. Who has the pen drive? Oh, yeah, so let's keep passing it on. The beginning will not require the data set, so you have a few minutes to quickly copy it. We will start with the toy example and then move to the physics data set. 9 to, okay, good. Okay, has everyone at least got the latest version of the notebook? Okay, so just to be very, very specific, so from the repo, you're going to go to SBI tutorial again. We did SBI 1 last time. This time we're going to do this one, SBI tutorial 2. So you open that notebook. Of course, not in GitHub, you open it in Jupyter. Right, and we're going to go through this slowly. Please ask questions for the parts you don't understand. You will see that all the neural network architectures here are super, super simple. So it's really the concepts that we're learning here. So you should ask questions. Okay, so the first line requires no explanation. It's just importing stuff. Then we're going to start omnifold on a toy problem. I should say that most of this content was originally developed by Vinicius Mikuni, who is one of the leading omnifold experts right now. He has worked on using omnifold to unfold data from the H1 experiment. Okay, so here, so we're again doing some more imports, train, test plate, backend, but then we're going to define a function called reweight. It takes the events you need to reweight as input, a model, which is going to be a classifier, and a batch size just so that it knows how many to predict. And then we see model dot predict gives us the output of the classifier. So what are the weights going to be? Can anyone remember how you get the weights once you train a classifier? Exactly, very good. Okay, thank you. So it's going to be f divided by 1 minus f. Oops. All right. So why is there? I'm sure some of you don't remember. So can you explain why it was f by 1 minus f? Exactly. So f minus 1 upon 1 minus f gives you the likelihood ratio between the two distributions. So if you have the likelihood ratio per event, if you use that as the weight, then your distribution will look like the other one. So this is a reminder. So if you have this distribution and you have this distribution, and I'm taking the likelihood ratio for this event here. That's really this height versus this height. And so if I use that ratio to weight, then this downweights this one, right? And so these events get downweighted, and then your distribution 1 starts to look like your distribution 2. Is this confusing to anyone? This is something we saw on Friday, but of course there's been the weekend, so feel free to ask. Okay. Then this is just binary cross entropy. You could use the regular one. Here we just make sure that like infinities and so on don't cause trouble, because yeah. So you can think of this as the regular binary cross entropy. The only thing to keep in mind is the way this has been implemented. The weights are not explicitly shown here. The weights are actually hiding inside Y true. So you can see that here the weights are extracted as the second column in Y true, and the actual truth is the first column in Y true, right? Besides that, it's normal. And this is the meat. This is where we define how omnifold works. So here, theta 0 g, theta 0, let's say, is your simulation. It's done at some parameter theta 0, which is our best guess, but it's biased. The true theta we don't know. So yeah, it's theta 0 g, g for generation, theta 0 s, s for simulation, and then theta unknown s, which is the data essentially. So it's s because it's detector, it's at the detector level. Then it takes the number of iterations you want to do, right? So you have two classifications in each iteration, and then how many times do you want to do it? And then you have to pass the model, the classifier, because you can define the architecture outside and then pass it to this omnifold function. And verbose is just about how much how much it complains, how much information it's going to give you. Right, and then there's some checks to make sure all the data set looks right. You start with defining just the structure of the weight matrix. You're going to fill them up later. Okay, and then labels. So labels 0 are, so this is for the simulation, we're going to label them 0, and for the data, we're going to label them 1. Right, because we want to reweight the simulation to data, so the data has to be 1. So labels unknown meaning data is 1. Right, and then you concatenate them for the observables and then the labels. And okay, weight pull and push in the beginning, we're going to say it's 1. If the Monte Carlo MC gives you some weights, then you use those weights instead. And you can just multiply them to 1s essentially. So the initial pull and pull, we're going to initialize them with 1, and then you'll see that they keep changing. And then we start the iterations of reweighting. So first, we want to classify simulation versus data. So the initial weights are just the pull weights. You do a train test split. You hide the weights inside this y, as we saw earlier, because the loss function expects it inside y true. You could do it differently. You could pass the weights separately, and then you compile your model with this loss function that you've written up above, and then you fit the model on your training set with the labels. Here it's been defined as 40 epochs and so on. You can change all of this. And then your new weights are going to be the original weights times the reweight that comes from the classifier. So this reweight function that we defined earlier, you give it the samples you want to reweight in the model, and it'll give you the new likelihood ratio, right? And then you multiply it to the original weights, and that's how you get the new weights. And that is what you save in this this weight matrix. I is the iteration. So in this weight matrix, you will save weights for every iteration so that you can do the plots afterwards. In the end, you only need the final iteration of weights, right? You don't need all the intermediate ones, but just for validation, you want to see how the weights are changing. So you save all of them. And so the weight matrix is three-dimensional. The first one is just to the number of iterations. The next one is the steps. So it goes 0 and 1. So the first step is 0, second step is 1. And then the last one is obviously the events. So yeah, so you save that, and then you go to step number 2. In step 2, you are training at the generation level with the new weights versus with the weights from the previous iteration. So that's what we're doing here. You can see the ones, because we start from ones, and then this the new one, train trace split as before, and you hide the weights inside y as before, compile the model, fit the model. I think it's the same number of epochs and so on. And then you get the new weights using the reweight function, and then you save them in your main weight matrix. So everything is the same iteration, but this is step 1 because it's the second step, right? And that's the end of iteration number 1, and then this loops over the number of iterations you want. One iteration is usually not enough, but for very simple problems, even 2 iterations can be enough, and for more challenging ones, you need to go to 4, 5, 6, all the way to 10. So how do you choose the number of iterations? You do the reweighting and you look at the plots. Okay, and at the end, what does this function return? It returns this weight matrix with all the weights from all the iterations and all both the steps. Okay, what are the questions about this big block of code with the omnifold definition? You're going to ask me later, I know, so I'll wait for that. My notebook is not running. Yeah, that's right. That's right. Yeah, so first time you train it for simulation versus data, reweight, then the model is trained again. And so then it predicts a different set of weights, which is to do the generation versus generation reweighting. Okay, good. My notebook is at least running. Yeah, okay. Then my question to you is, if you paid attention during the slides, there should be something here that's confusing to you. There's a little sleight of hand that's happened here, and it's very much related to the question you're asking. So maybe this is where the question is coming from. You're thinking, wait a minute, the whole power of this method was we train a model apples to apples. So detector level versus detector level, and then generation versus generation. And the power there is you can have different observables at the detector level and at the generation level. You could have some stuff that you, at the generation level, some observables that you cannot reconstruct, right? So there's no one is telling you in Omnifold that you need to use the exact same set of variables for the 2 classifications. So in fact, often you will have a very simple dense network for the generation level because you can create all your observables there. But at the reconstruction level, you'll have graph neural networks or something because you hope that the network will do the reconstruction internally, right? So you have a very different network for the first step, a powerful one, and for the second step, you don't need such a powerful one. Here we have just one model. And this is only for the tutorial. In reality, you will probably train 2 separate models for the 2 separate steps. Here, because you will see in both examples that the number of observables and even the nature of these observables is similar at both steps, we can get away with using the same model, and whatever it learns from step 1 is kind of carries forward for step 2. So but in reality, you will want 2 separate classifiers. Okay, so for the toy data set, we're going to generate 4 samples. There's the truth, which is nature. Then there's the nature reconstruction, which will include detector effects. And then the synthetic, as in like simulation detector effects and simulation truth. We see that here we have 10 to the power 5 events in each. So what is happening? This is your, at the generation level, is just a Gaussian 0.2, 0.8, right? What happens at the detector level? At the mean level, we are smearing it with another Gaussian, right? So I guess the theorists amongst you will know that we spend a lot of time doing Gen 4 simulation, and then you just approximate it with simple smearing. So that's roughly what we're doing here. Whatever is the truth, like if there are sharp distributions after the smearing, they become broader because of this. Right, and then there's the so this is the, yeah, both of them together, and then this is, we're going to pretend this is data, which is not the same as your generator. So the generator was 0.2 and 0.8. Here, it's a Gaussian at 0 and 1, right? So there's a bias in your generation. And we need to overcome this bias in the unfolding. Let's see if we can do that. And then, of course, again, the simulation or the detector level data that you actually observe will include this detector effect, which is the same as the one you applied on your generation, is the same smearing, all right? Yeah, perfectly. You know the, yeah, exactly, exactly. You know, at the moment we're pretending you know your detector simulation perfectly. Right. So yeah. So what you've noticed is that the data truth and the MC truth are not the same. So it's not a trivial problem. There's a bias, and then the detector smearing is the same. And of course, since we are only going to use this data truth to validate the procedure, but we don't have it in the real world. When you actually apply it at the LHC, you will not have that. So you better not use that somehow in your training. So keep that in mind while we see the next steps. So first, let's look at the plots. So this is what it looks like. You have the MC truth is this blue distribution, and then the data truth is broader as we, it just happens to be because we have different, there are different Gaussians with different parameters. And each of them then goes through detector effect. So the MC RICO is broader than the MC truth, and then the data RICO is broader than the data truth, which is what you expect from detector effects. And what we want to capture is reweight these samples, these blue samples, to look like the yellow samples without ever having trained on the yellow samples. So now we're going to define a model architecture. I'm not going to explain it. We've seen this hundreds of times. It's a very simple Keras dense neural network. Classifier, so only two outputs, the binary cross entropy. Yeah, we're calling the model Gauss because it's a Gaussian problem. And now we're going to run only 2 iterations to begin with, so that it's quick. You are free to change this number to anything 5, 10, and see how that affects your results. But you have to fill in something here. So what do we put in here? There are 3 inputs that go into the omnifold besides the number of iterations and the model itself. Can someone tell me what the first one should be? Monte Carlo? I don't have anything called Monte Carlo. I have these terms. Okay. Next one. Last one. Theta unknown S. Yes. And not theta unknown G. That one we don't touch. Okay, just to confirm, let's look at how omnifold was defined. G, S, and unknown S. Okay, hopefully that works. So now it's calling the function we defined earlier. it's doing step 1, so it's training the first classifier. And then, yeah, it'll copy the weights to train the second classifier. The whole thing it'll do twice, and then it'll output the weight matrix, the 3-dimensional weight matrix, which we're calling my weights. And then we're going to plot the unfolded distributions. So I think I've left gaps here, or have I not? I have. Okay, good. So what are we plotting? The first thing we're going to plot is theta 0g, which is the generation distribution. We're going to also plot the truth, which is the unknown g with data truth. And then this is the interesting one, the unfolded distribution, right? So how do we plot the unfolded one? As I said, you are going to reweight the MC truth. So the events will be the same as the first histogram, theta 0g, but they're going to have weights. The first one is without weights. This one has weights. And the weights is equal to my weights, and you have to fill in the which. So the first one is iteration. Which iteration do we want? The last one, right? Which step, 0 or 1? Yeah. So yeah, exactly. You want the final last set of weights, because those are the best weights you're gonna get. You want it for all the events, and you want to plot them exactly the same way as the others. So let's do that. And so this is what we get. So you can see that these events have been reweighted to look like the black. This is after reweighting. It looks like it's the black distribution, and the black follows the yellow one pretty well, right? But not perfect. There's a discrepancy here, but I would say it does a pretty good job for only 2 iterations on a very simple network. It's also a simple problem, so you expect a simple network to work. If you are interested, you can now go up and change now iterations from 2 to 5 and see if that improves your results. Okay. So for me, the training is taking a little bit of time. I guess for you also, it's going to take time since you're running on your laptop. Meanwhile, I guess some of you've noticed that there's this kind of unfolding method is a bit funny because you don't, in the end, report the data events themselves. You're actually reporting Monte Carlo simulations as your unfolded result, right? You're saying these are my simulations, and these are the weights. And if you apply the weights on the simulation, I claim that this distribution will look similar to what the truth should be. But I have never given you the actual data events. So it's a peculiar thing that you feel uneasy about in the beginning, but then you get all right with it. Sorry? Yes, that's right. Yeah, absolutely. So you should not feel uneasy because the weights are coming from the data. Yeah, no, exactly. Yeah, okay. So if it feels natural to you, that's great. To me, it didn't, and I had to convince myself for a while. But yeah, of course, yeah, it's good. So it's always, I think, the younger people are able to pick up things faster. So it's great. I think there was a comment by Feynman or something as well that like the younger generation learns quantum field theory without as much objection as the older people. So. Okay, so we see that after 5 iterations, it looks better, right? I think everybody agrees that as the more iterations you run, the more we remove this original bias and move towards the data. If we were to run this too many times, and okay, we have enough training data, 10 to the power 5, but in a real experiment, the data might be much smaller, and then you would start to see that if you run too many iterations, then you'll get very choppy looking distributions that are really trying to maximize the likelihood way too much. So that's not something we'll do now, but if you want, you can reduce the number of events for data to something like 1,000, and then run 100 iterations, and you'll see that at some point things start getting worse because it's not smooth anymore. But for that, you need to have a powerful network as well. Okay, and what do the weights say for, so you can, since we're plotting this at the unfolded level, so without detector effects, but now that you have the weights, you can do the same plots at the detector level. And again, you see that, okay, now MC Rico is here and data Rico is here, and of course the omnifold reproduces the data Rico reasonably well. To keep in, you can keep in mind that step 2 was, so step 1 was data matching simulation to data. Step 2 was generation to itself. So this is after step 2. So it's not a trivial thing. So it means that the omnifold has really converged, and even after doing a step 2, the black continues to look similar to the reconstructed data, the observed data basically. Right? So if this is different, it means your omnifold iterations are not enough. You need to do more. Right? This is a useful validation plot to have to look at. Yeah, the model has to take the weights. Model has to take the weights, otherwise it will not learn, because these are just Gaussians. So if you don't see the weights, then it doesn't see the difference in distributions. The weights are everything. So you can see. Let's look at the. Yeah, this is the loss function we've defined, and here are the weights and the loss. Okay, yeah, we should have gone through this in detail. So yeah, thanks for the question. So the loss is really, this is your binary cross entropy has been written down explicitly, and it's weighted by the loss. I mean, weighted by the weight, right? Yeah, the weight is essential. Without, if the training was blind to the weights, none of this would work. This is the weight, this is the latest weights you have. This weights will keep changing. Yeah, it's the previous step, yeah. Very first step, it's just once. In this case, it's just once because we are pretending, yeah, data is 1, and then we're saying the simulation is also 1. In reality, your simulation will have some MC weights, so those will be the weights. Yeah. Right. Yeah. So in fact, what is changing? Almost nothing. The X, the observables stay the same. Y, the labels stay the same. The only thing that changes from iteration to iteration are the weights. And so that's what the network is learning. So really, it's only the weights that affect the distributions. So in fact, this is a question that comes up often that, oh, I don't think, like when we teach machine learning in the beginning, people think that the weights don't really have a contribution to the learning, but it absolutely does. Because here nothing is changing apart from the weights, and you can see that the model learned something new. Okay. Okay. Any more questions on the toy problem? I see murmuring, which is usually a good thing, but you can ask me. Okay. Now we're going to look at a physics data set, and this is some deep inelastic scattering data set from an H1 experiment. I know nothing about this experiment, so don't ask me about too much detail about the observables. Just one thing, yeah. Don't I can read the observables the same as you, something eta, something phi. But yeah, point here is that we saw a one-dimensional example, but to really see the power of unbinned multidimensional unfolding, I think you need to see an example on multiple observables. So we're going to run through this. This data is from uh, like, yeah, it's not easy to find a data set that's public and open. So we're using these people have been kind enough to let us use this for tutorials. So we're going to use their data set. And we're going to see a few things. Yeah, we'll see how the performance is on a real physics data set. And also, at the end, we want to see if all the things I've claimed about omnifold are true, which is we're going to unfold these observables, and then we're going to look at the distribution of a new observable, something that we did not explicitly unfold. And we want to see if this new observable has also been unfolded for free or not. Right? So this was the whole selling point of ML unfolding compared to traditional methods. So we want to make sure that that's actually true. Yeah. What can be varied? Bin size can be varied. Yeah. Uh, where in our method? Yeah, because we're only using histograms to plot at the end. The actual things are still events, so they're unbinned. So yeah, you could definitely make this. You want to make this plot in higher binning, you can do that. It's trivial. Um, yeah, yeah. Yeah. Okay, so then you're dead. You can't do it. If the data is given to you as a histogram, it's over. Which is the whole point. We don't want to give the data as histograms to theorists anymore, because then they are stuck with that bin width. So instead, we want to give them events, like events with the weights that reflect the data as we discussed. Or I mean, if you don't want to think of them as events, you think of them as just like infinite binning. Point in the phase space. Yes. Okay. Very good. Yeah. Can you repeat that for? Point in the phase space with the weight. Yeah. Point in a phase space with a weight. Yeah. So if you have that, then you can construct any binning afterwards as you like and do your studies. We know for certain processes, the phase space is having fixed dimension. For two-dimensional process, so two-dimensional process is two-dimensional. Phi and theta is the only two. Yes. For n particle final state, it is 3n minus 4. Okay. Okay. So what? So do I have to match that? This is the maximum number of the phase space. So less than that, it is fine. There is some freedom. But if I use more number of features to match, very good. Than the phase space. Yeah. Okay. So then I'm kind of over constraining. You would think that. Okay. So this is a very, very important point. So what if you are using more observables to unfold, then you actually have degrees of freedom? It still works, because if like you could just give phi to 2 times, and it'll learn that okay, these are fully correlated, so the way I unfold this observable is the same way. So you can give it more observables than, yeah, it'll learn the correlation, and it'll learn that the degrees of freedom are smaller than the number of observables given. Yeah. Yeah, and it's an important point that I didn't mention. So this is good. All right. So I'm really hoping that at least 70% of you have the data set by now. Can I just get a rough estimate? I put up your hand if you don't have the data and you're waiting for it. That's really good. Awesome. So yeah, I don't know if we put instructions for H5 pies, but if you don't have this H5, just do pip install H5 pi and it should work. And then, so I've asked you to put the data set in this folder, unfolding data in. So I'm going to give you a second to put it in the same. So it's going to look here. So if you're in the SBI tutorial, you're going to have this folder called unfolding data. And if you go inside, you have the Django and Radgap. So if you could place the files in this structure, or you just put it wherever and put the path here, we should be good to go. All right, so let's see if you can open the files. So yeah, these are the observables. This is the hadron PT eta. I think it's the electron E Z direction momentum eta. And yeah, so here we're using the same observables at both the levels, but this is not a requirement. You can really have different sets of observables, different neural network architecture, and usually that is what you do. You have a much more powerful architecture at the detector level than at the generation level. Okay. Yeah, and since this is a physics data set, you have to do at least some minimal pre-processing. This is very simple stuff, just mean and variance. Afterwards, if you like, you can, as before, you can always improve your pre-processing. All right, so the unknown again is your data. So in reality, of course, you're not going to have the unknown G, but here both of them are simulations. One is called RapGap and the other is called Django. This is similar to, maybe for you it's more familiar, like doing Pythia and Herwig, right? So these are two different kinds of generators, and then you use the same detector simulation, GEONT4, and then we're going to pretend one of them is data and the other one is our simulation, right? Because we want to be able to validate. In reality, you will have only one of them, and then the other will be real data. Okay. So for this study, your data at the detector level you get from the first line, observed features for the natural data set, and at the generation level, as in the truth that we want to try to estimate, is this one, the gen features. And then for the simulation, I think this is a RapGap. We're going to use RapGap. So again, so here you generally expect to have the simulation level and the generation level examples. And okay, so I'm just removing unnecessary rows. We run this here. So, and again, further simplification, we're going to have equal number of events for data in MC. And then let's just have a look at the distribution of the observables before you do any unfolding. Okay, so what do we see? First, okay, ignore the last box. This is just because there's nothing there. So yeah, we see in some of them, so the blue is the MC truth, which is biased. This gray thing is the reconstruction, and the yellow is the truth, the data truth that we want to estimate, and then this darker one is what we actually see at the experiment. And sometimes they're all pretty close to each other, so then the reweighting is very, very small, and sometimes they're very different, right? So here also, like both at the gen level there's a difference, and then at the RICO level there's less of a difference. But the RICO and the gen level distributions look very different, which is fine. The detector seems to have a large impact on this observable. Okay. So again, we're going to define a model, simple Keras model, and the same model will be used for both levels. And this time, because it's a harder problem, let's start with 4 iterations and see how things go. Right, so everything else is the same. We just do a pre-processing of the data before we feed it to the networks. But besides that, we are again calling this omnifold function, right? And we're giving it the same inputs as before, the generation level and the simulation level, and then the data iterations. What do we put here? What was the last thing? Which model? Yes. I'm asking just to make sure people are paying attention. Let's run it. Okay, while it runs, it's going to take a while. Have you guys been able to open the data file? Is it working? Yeah? Okay, cool. All right. Yeah? Okay, it's pretty slow. I think 10 to the power, wait, let me see. 6, yeah. It did run yesterday. I tried everything. It just takes a few minutes, but it's not. We'll finish on time. Suggest. I I cannot sing or dance. But, yeah.
Meanwhile, we can
Yeah.
entertain some questions then.
Yeah, absolutely.
So,
Yeah.
and you nicely said that we can have more number of distribution than the degrees of freedom.
Hmm.
If I have more, does it help more? Because
Yeah.
we know that when we have a lot of weak classifiers, so whole classification becomes
Yes.
better.
Yes.
Although each one will have some error
Yes.
because of propagation of error.
Yes.
So even in the data, I measure something and then I reconstruct something.
Yeah.
And more variable I construct, more layer of
Yeah.
thing apart, the error propagates, and whatever I have has each one has some error.
Mm-hmm. Yeah.
So I'm adding more and more suitably errorsome variables, but all of them provide me kind of weak losses.
Yeah, I guess. Yeah, I think like so. You're saying adding more input variables, right?
Adding more input variables,
Yeah.
much more than the degrees of
Yeah. Yeah. So for sure, so it'll help, and it'll help in the sense that let's say there are some like let's say you put a 4 vectors of a particle, right? In principle, from the 4 vectors, it can calculate everything else. But if you know that okay, there are these 2 particles, and if I calculate the invariant mass, then that is the important quantity. Then you can calculate it by hand and give it as an additional input. This is fully correlated. I mean, from the 4 vectors of the 2 particles. But giving that additional information definitely helps the unfolding procedure. Yeah, and we've seen that. Like we were doing this very hard top data set where yeah, you had to like reconstruct it from many different things, and giving that as an input really helped. Even when you had a lot of data, it still helped the training. Yes. Yeah, so the more you give, the better. And in fact, yeah, since there are correlations, instead of unfolding a single observable, like if you really care only about one observable, and you only unfold that, compared if you unfold that with a few others, often you'll find that that single observable is unfolded better because of the information it gets from the other observables.
Because sometimes back we had this discussion, like what if the variables are correlated?
Yeah.
So do the PCA first and then
Mm-hmm.
not.
Not here, not here. Yeah, depends on the application. Is somewhere else you might want to do PCA. Here you want the correlations. You want to use it. Yes. Yes. And the other thing is, what about uncertainties? Let's say your data here, for simplicity, we have 10 to the power 6 each. But let's say your data is 10 to the power 3 and your simulations are 10 to the power 6, right? So you've reweighted your simulations to look like data. But now you have 10 to the power 6 events. Okay, they're weighted, so their effective sample size is smaller. But but you can't get more for just for free, right? So then you have to account for the fact that you've reweighted a huge bunch of simulations to a small data, and so the statistical uncertainty that you get just raw over there will not be correct. So there are things you need to do to account for that. There is a specific kind of training you can do that forces the weights to not just um, reflect the data, but also reflect the statistical uncertainty in the data. I haven't gone into that, but I can show you the paper that shows that. Another method, which is more expensive computationally but more robust, is instead of doing the unfolding one time, this is the case in all SBI methods. Instead of doing it one time, you do the whole thing like 100 to 1,000 times, which is very, very expensive, and we do it in supercomputers. But then you get like you get a different unfolded distribution from each procedure, and then the variation between them can give you some kind of uncertainty. And then you can do bootstrapping to further get the stat uncertainties on the unfolded results. And nonetheless, even this ignores one other kind of uncertainty, which is something we don't talk a lot about in physics, but it's common in machine learning, which is called epistemic uncertainties. These are the uncertainties of the model itself. What if the model is not well trained? And here, we've usually found that the epistemic uncertainties are very, very small and can be ignored compared to stat uncertainties. But in some cases, in pathological cases, you can create them where the model is just so poorly trained that the model uncertainty dominates, and then you have to account for those as well, which also you can do with training many models. Okay, it's still running. It's only the first step, first iteration is done. For you? Oh, for me, yeah. Even longer? Okay. Hopefully, at least for me, it runs. I'm on a GPU, but of course, dense networks are not that much accelerated by GPUs. But yeah.
You are having about 0.7 microsecond per step.
Yeah.
5 microsecond per step.
Wow. Okay.
0.1 for you, 5 for me. 0.7.
Okay. Okay. So it's huge.
So it is at least 7 times slower.
Okay.
My GPU refused to recognise. I have a small GPU.
I see. I see. Okay.
Something happened in the
Installation. It was working before and it stopped working. I see. Okay. Are there any other questions about this while we are waiting? Or comments? Has anyone done unfolding in their analysis? You'll do it soon.
The first time I saw differential distribution of GPU unfold.
Yeah.
So I was so happy to see it in that 2007. Then I'm not asking for something really big. I was really afraid to talk to experimentally. Can the reverse be done? So I used to talk among the theorists, and then they said, "Shut up, how difficult it is to."
Interesting.
So this was said to me by theorists, but then experimentalists were thinking. And then I directly, first time I saw was directly published.
In 2007?
2007.
So that's fascinating.
But it must be happening before. It's just that I wasn't interested in anything.
Oh, okay, interesting. Yeah, I think these methods have been around since before 2007 for sure.
Yeah, but in 2000 it's a development data.
Yeah.
Before that there was no unfolding.
Yeah. Yes, that's the IBU method. Yeah. So yeah, that's another method that can remove the. So the before ML unfolding, there were two popular methods: the matrix inversion, where you build a matrix of the bins at record level versus bins at generation level, and you just learn a mapping. And then there's this the one that Sanmay mentioned, which is iterative Bayesian unfolding, and this does something very similar to OmniFold, but in histograms and and then it does it over multiple iterations, and it can handle biases in your simulation.
In that analysis, bin migration used to be.
Bin, yeah.
But since we are waiting for it, things slightly now.
Yeah.
Which is like, suppose I have nothing but binary distinct, and I define that I don't want to go granularity smaller than, let's say, certain number of fields. Okay, and I train my this thing tree on so there is no training like signal versus background kind of, but I'm just want to say make sure that I build the multi-dimensional phase space or whatever into as smaller bit by dividing such that the smallest leaf, so to say, doesn't have a number of event less than certain. I'm kind of creating a distinct multi-dimensional histogram.
What is the criteria for the training?
Criteria stopping point is single that the number of events should not be less.
But what is the loss? Like, are you doing classification?
No
So
just divide.
just divide. Okay.
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 So how would you, what is the right way to divide? I don't know. I just do random.
Mm.
And it's like random forest. I have many of them.
Mm-hmm.
So and then I get a score that which one is best parameter to divide. And using this bias, maybe I divide it. I'm
Okay.
just thinking about.
Yeah.
So I have a multi-dimensional histogram way for the one set and for the other set. And I know which bin it sits here. No, not for the other set, I use the same bin. And I say, here is my simulated data. When I do detector simulation, it moves this.
Yeah.
Okay.
Yeah.
So this is the transfer, so to say, I learn.
Yeah.
Okay, I map it out. And so know that most like, so I keep it kind of distinction.
Yeah.
So when I know that event, fell, experimental event fell into this particular bit, what is the transfer probability?
Yeah. So you can get that from your simulations. So you can, you can be clever about making your bins, and then, because this is not my area of expertise, but yeah, you make. Do you know matrix matrix inversion very well, or better than me? Yeah, rough. Yeah. Hmm. Yeah. Mm-hmm. So if you would, let's say you've decided these are the bins, however you defined it, then so this is at the RICO level, and then this is at the particle level. Yeah, whatever, truth level, MC level, and then if you and you can fill this histogram with events that are going like this, and then calculate the probability as you said. Now, if it's 1 1 1 1, life is great. Yeah. And then everything, yeah, but as soon as it's not, and it's 0.8 and whatever, I don't know, 0.2, so like some of the events don't from this bin migrate to this bin and so on, then you can construct this response matrix, but you're doing it using simulations, and then you are biased by any, yeah, yeah, and that's why this IBU method is sometimes preferred over this method, because it can handle this bias, but it's yeah. Yeah, and in fact, there's a I guess another way to look at it. One is unfolding, which is you take what we have at the experiment and you unfold it for theorists. The weakness of this is you will never have the data at the detector level will be more powerful than the data that is unfolded. You can only lose information or be equal at best. You can never gain. So if you really want to make very tight measurements, you want to do it at the detector level, not at the unfolded level. And so there's another thing that we are doing called recast, I guess. You're familiar with that. So there, at least the big picture is we would like all the analysis we develop to be recastable. So you can, so we will publish some results for some study, and then you could plug in a new signal model or a new theory model and just run the simulation and see. So then run the detector simulation, and nobody has to optimize the analysis again because we don't have time, but you can run these new simulations and see how it would affect. Like if that was the truth, then what would your limits look like? And by looking at the output of the analysis, then you can set limits on this new theory without having experiments do the whole study again. So this in Atlas now, I think all SUSY analyses have to be recastable. So yeah. Yeah, yeah. No, it is not. Yeah, yeah. So it's better than like I guess it's a step in the right direction. That if you're lucky and your phase space is the same as that SUSY search, then it's great. Yeah. Otherwise, of course, we have to do the study again. But it's I think there's like they're twins or like maybe two pieces mirror. Like there's unfolding and then there's recast where unfolding we lose power in the sense that we have yeah, by unfolding we lose power. But on the other hand, in recast you have the detector thing, but yeah, you don't have the same phase space. Okay. So okay, I think my training is complete. Yours will be complete eventually. But since I know I'm eating up on your break, so let's do this quickly. Let's make the plots. Hopefully, I haven't left any things. Yeah, so here you can see this is the unfolded distributions, and you can see, okay, it's hard to see the differences, but like on the last one, you can see that the data and the omnifold results, the data truth and the omnifold results match. And so the omnifold is closer to the yellow than it is to the blue, which means it's correctly reweighted your distribution. And so this is the distribution we will report to theorists. Cool. But now, as a last final exercise, and then or we can even should we? Yeah, let's just do it now because yeah, in the next session you'll do something else. Now let's try to we've unfolded these whatever 5 observables, but now as you're a theorist 10 years down the line and you realize, wait a minute, the observable I really care about is whatever this is, this sigma e, or which is defined like so, right? And this theta, which is whatever this is. So let's try to build those observables from the unfolded observables and see if they also are unfolded correctly or not. So how would this look like? So just because I don't have time, I'm going to see if I can find an older version. Let's see. I think this is the same one. Ah, good, good, good. So normally I would have asked you to construct it, but we don't have time. All right. So you're seeing that we're constructing a new observable, which is at the gen level distribution. Yeah, you take this observable minus this observable, and this other one is 2 times arctan of whatever this observable. And then we do the, it was right here, okay. We do the same for the data. the truth. And then let's plot it. And what do we see? That even though these observables were not explicitly unfolded, you can see that we're doing, so see here, the black is matching the yellow one better than the blue one. Here we see that it's not doing so well in this phase space. If you can see that slightly, there's a discrepancy between yellow and black, but nonetheless, I think the black is matching the data better than just the raw MC. So, sorry? Yeah. Yes. Yeah. So you're saying it's obvious that it works. Yeah, no, you're right. It is obvious, but it's already this is so if you had done the old ways of unfolding, you would have unfolded histograms in certain bins, right? And then each unfolding procedure takes time. So if you wanted to unfold 5 observables, it would require 5 unfolding procedures, right? So maybe the experiment wouldn't have done 5; they would have done 1 or 2. So you wouldn't be able to, you might not be able to construct this. Even if you could, then you would be stuck with histogram bins. So doing arithmetic with like the bin center, you're going to lose precision, right? The distribution is not going to look the same. So even if it's a linear thing, already the fact that you're doing multi-dimensional unbilled unfolding, you can do this better than if you had to do them individually using histograms. Yeah, and then another one is the second one is more complicated. So yeah, 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 and depending on the problem and stuff, like you can do more. You can take 4 vectors and construct something in like an invariant mass and see if that's been unfolded properly or not. There's more you can do. But since we're over time, I don't want to, yeah, there are a few other exercises we could do, but we don't need to. I think hopefully I've demonstrated the power of ML unfolding and convinced you that it's useful. It's not just some fun ML toy. It's actually lets you do better physics. Yeah, so what are your questions on this final part? Yes. Yeah, that's a very, very good question. Should we just dump as many observables as possible? Naively, you would think yes. There are some pains in actually trying to do too many observables. And sometimes you want to restrict to only the phase space that you care about. Because if you're unfolding it, you better unfold them all well. And sometimes you'll see that like if you put too many, then you're not able to unfold one thing. So you really have to optimize the architecture. That's pushing your entire study back 6 months. And no theorist cares about getting like these 90 observables correct or something. So then you can start dropping them off. So there's a practical reason why you often we use only a few, but that's right. In principle, you could do a huge number. Also, different methods scale differently. If you just use dense networks, it's not going to scale that well. So when depending on the data, like how it is, you often will use a graph neural network if you have variable number of jets and so on. And all of these, you have to look at the scaling ability of these models themselves. And this is also one of the reasons we are even though Omnifold works so well, we are still investigating generative models because things like diffusion models can often scale better to high dimensions. So yeah, these are questions we will be continuing to answer over the next 5 to 10 years, maybe 5 years. Yeah. Last chance. Any other questions? Of course, we can talk in the break. All right. Okay. Thank you very much. This is the end of SBI, and after the break, Elham will do generative models.